Okay. All right, so hello everyone. Today we're just going to finish the discussion that we were making last time about determining the number of ordered pairs that have a specific least common multiple. Okay. I am just going to present you the gist of all that we did. Okay. And so that we can actually go ahead and finish the objective that we started at the beginning. Okay. So so to give you just the gist of the algorithm of what's happening is our goal is to figure out all of those pairs here. That's what we're trying to do. We want to figure out all of those pairs that have a specific least common multiple. And as you can see, here we have just listed all of those pairs. If you see, the least common multiple of this is 12. Okay. And that is true for all of those pairs. But our goal in all of this discussion was to find a way to figure out the number of the pairs without having to go through all of this process of listing all of the possible ordered pairs that we have. Okay. So that was the reason for the whole discussion that we started. So and what we actually figured out was that each of those pairs has a very specific has a very interesting way to be written. We can just write it, every one of those pairs. We can write it in like this, in this form. So so if you notice all of the pairs, all of those pairs, let me write also this one. All of those pairs can be written in this form in some way. Okay. So so if I just went ahead and wrote it down, let me see if I have it here. All of those pairs can be written like this, actually. Okay. They have a way to be written such that they are 2 to some power times 3 to some power, and then 2 to some power times 3 to some power. Okay. This is from the discussion that we made. Okay. And what we talked about was that instead of going ahead and counting how many are those pairs, because we care about how many they are, we don't care about what they actually are. Instead of going ahead and counting these ones, we would go ahead and count all the choices for the exponents of 2 and all the cases for the exponents of 3. Okay. So let's see, can somebody remind me, just by looking at this diagram, what are the possibilities for the exponents of x and s in those examples here? So what are the possible pairs x and s that I can have? I keep saying 12. I want the specific pairs that I can find here in this specific example. Yes, 0, 1, and 2 is fine, but I want more specific. For example, one pair would be 0, 2, because you see here is 0 and here is 2. So one pair would be 0, 2 for those exponents. What other pairs do I have here? Yes, I like Angelina's answer, but let's put it in pairs as we see it here. So one pair here would be 0, 2. Here another pair would be 2, 0, if you see. So what other pairs like that do I have? Yes, 15 is fine. But I'm now interested in figuring out only those specific pairs. So see here, for example, I have 0, 2. See, here I have 2, 0. Here I have 2, 2. So I'm just trying to figure out all of those different pairs that I can have. Okay. And if you notice, we don't have many of those. These are the only possible choices for those pairs, right? And in the similar idea for y and t, for those pairs yt, again I have only very few choices. I have the choice 1, 0, 0, 1, and 1, 1. Okay, those are all the choices that I have. And if you notice, these are 5, and these are 3, which means that the number of ordered pairs will be the product, which is 15 pairs. It is exactly how many pairs we have. Okay. So the discussion we made. So after the discussion we made, we found a good way to figure out how many those pairs are in each case. Okay. And what we actually figured out was that we have this very nice formula to figuring out all of those pairs. We just look at the power of the specific just look at the exponent of the specific prime number, and the number of pairs of this form are 2 times n plus 1. This is what the discussion ended up with. Okay, which means that since in this specific example that we were doing, the factorization for 12 was 2 squared plus 3 times 3, then that means that the cases for x and y would have to be 2 times 2 plus 1, which is exactly what we found, 5. And the cases for xs. And for yt, the cases were 2 times 1 plus 1, which is 3, because this exponent is 1. Okay, so the total number of ordered pairs was 5 times 3, which is 15. So this was where we ended up the discussion last time. We actually figured out that we can immediately understand how many pairs of this form we have for each exponent just by using this. We multiply the exponent times 2 and we add 1. Okay, so using this idea, let's try to do this problem here. Okay, so we want to determine how many ordered pairs we have with a specific least common multiple. Okay, and just for our convenience, here is the least common multiple. Okay, here is how we can write it in a prime factorization. Okay, so what will the ordered pairs look like that we're looking for? If you remember, in the last example, they had a very specific format. So what format are they going to have now? Does anyone want to try? Okay, so the idea was that since the prime factorization is 2 to some power times 3 to some power, then the ordered pairs would be of this form again. Let's see. Of this form, okay? Just exactly like in the last problem that we did. The only difference here is that we are allowed for more pairs, said because we have higher exponents, okay? That is the only difference. So the ordered pairs have actually this form again, okay? Okay. So they have this form. Now, can someone try to figure out the possibilities for x and s? So for the exponents of 2. we had found a convenient formula for this one. So the number of these pairs is actually 2 times whatever is the power of the exponent plus 1. That's what we figured out for the last discussion, okay? So how many possibilities would I have for the powers of 2? Two to the 7th, you're saying. Where did the 7 come from? 7, yes. 7, because I have 2 times 3, because the exponent of 2 is 3. Okay, that's a 7. So for the choices of x and s, I was actually going to have seven cases, all right? 7 cases. All right, so that's good, 7 cases. And here are the actual pairs. If we were to sit down and find them, those would be the pairs, okay, for the exponents of 2. All right, they were just all of the pairs that have all the possible entries that are smaller than 3, their mirrors, and then 3, 3. Okay. All right, so that is what we have for the choices for 2. Now, what about the choices for 3? How many are the possible pairs for the exponent of 3 this time? 5, I see, Angelina, nice. Because we have 2 times 2, because now we have an exponent of 2 here. So we're going 2 times 2 plus 1, which is 5. Okay, so very nice. So I have 7 cases for the exponents, for those exponents here, x and s, and 5 cases for the other exponent. Those are the pairs. 12 is total. Careful. Careful. We're not interested in adding them, because we're going to find all of the ordered pairs that have simultaneously these cases and these cases. So we actually care to find how many they are, because we're going to be using one pair of this and one pair of this in its time, right? So if you're going to build this one, you're going to be using one pair for this, let's say, and one pair one pair for those cases, and one pair for those cases. Okay, so you're not interested in adding them, you're interested in multiplying them here. Okay, because this is going to give you the total number. Imagine that you have how can I take you back? Imagine that you have one pair here, one pair here, one pair here. We found 7 of those for the powers of 2. Right? So you have 5, 6, 7. This is for the powers of 2. And for the powers of 3, we found that you have 5. So you have 1, 2, 3, 4, 5. Okay, so to find the total number, you're not going to add them to add the number. You're going to think how many different combinations you have of those. Okay, so I can combine this with all of these pairs. And then I can combine this with all of these pairs. Okay, so this is not an addition, this is actually a multiplication. Okay, so I'm going to actually have 35 ordered pairs, okay, in this case. Okay, because after I figure out how many pairs I have for the power of 2 and how many pairs I have for the power of 3, then I care to find how many combinations I can make of those. Okay, so that's why I multiply them together. Okay, and now what if I asked you about the unordered pairs? Well, to figure out the unordered pairs, we have to slightly go back. We have to go back to the specific example that we had here, let's say. And here we had 15 ordered pairs, okay? How many are the unordered pairs in this case? Well, if you notice, to find the unordered pairs, I just have to go ahead and subtract this guy because we don't count him as an unordered pair, okay? And then I just go ahead and cross out all of the mirrors. Right, I cross away all of the mirrors. So at the end I have, for unordered, I have 15 minus 1 divided by 2, which is 16, which is 14 divided by 2, which is 7, okay. 7, nice. Okay, and that's generally the idea for the unordered pairs. To find the unordered pairs, I take the number of the ordered pairs, I subtract this guy, and then I divide by 2 to kill all of the mirrored pairs. Okay, that's exactly what we did in this last problem that we were doing. In this problem that we're doing here, we figured out that the ordered pairs were 35, and to figure out the unordered pairs, we go ahead and subtract the one that is 72,72. So we're subtracting this pair. And then we're dividing by 2 to kill all of the mirrored pairs. And that is going to give us 17. Yes. Okay. So that is the method in very short. Okay. That is the method that we're using. And the last thing I'm going to do is to try and use this method to figure out how many ordered pairs we have that have this least common multiple. Okay. So this is the last thing we're going to do because this was the objective that we wanted to do all along. Okay. Okay, so let's start. Does somebody want to try and tell me the form of the ordered pairs that we're going to have here? How are they going to look like, the pairs that I have here? Well, to figure out how they're going to look like, I just look at the least common multiple that is given like this. I'm going to have some power of 2 here times some power of 5 here times some power of 11 here. Okay, because this is my least common multiple. And same goes for the second part of the pair. It's going to be 2 to the s times 5 to the t times 11 to the u. Okay. This is going to be the form of my ordered pairs. And I just have to figure out how many possible pairs I have for x comma s, which are the powers of 2. How many pairs I have for y comma t, which is the powers of 5. And how many pairs I have for the power of 11, which is e comma u. And then I'm going to multiply those together to find all of the different combinations. Okay, that's basically what the discussion comes down to. Okay. So what are the choices for x and s? Let me write again the pair. It's going to look like. It's going to look like this, and then 2 to this times 5 to the t times 11 to the u. Okay. So what are the choices going to be for the powers of 2? Anyone wants to try? It is the formula that we talked about the last couple of minutes ago. 5 and 5 is Angelina saying, but how did you figure out this 5? What formula did you use? Yes, but the power of 2 is 3. We're using the power of the exponent to figure out how many they are. Yes, it is 2 times n plus 1, but n is the exponent. It's not the actual number itself. Yes. So the choices for the exponents x and s are going to be 2 times 3 plus 1, which is 7. Okay. So we had 7 cases for x and s. Right. Okay. So for x and s, we have actually 7 choices. What about y and t, which is y and t are the exponents for 5? How many cases do we have for that? Yes, it is 15 because it is 2 times 7 plus 1. 7 is the exponent of 5. Okay, nice. So that's 15. Okay, so we have actually 7 choices for the powers of 2 in the pair. And we have 7 choices for the power of 2. And we have 15 choices for the power of 5. Okay, and for the power of 11, it is 27. That's great. We have 2 times 13 plus 1, which is 27. Yes. Okay. So actually, what we have figured out so far is all of the pairs. Yes, Angelina. That's the finish. Yes. So for all the pairs that we have that are gonna look like 2 to the x times 3 to the y times 5 to the y times 11 to the z, and 2 to the s times 5 to the t times 11 to the u, we figured out that these pairs, x and s, we have 7 cases for those. For y and t, we're going to have 15 choices. And then for z and u, we're going to have 27 choices. So then we were interested to find all the different combinations that this can produce. Okay. So the ordered pairs are actually, as somebody mentioned, it's 7 times 15 times 27. Okay. And whatever this produces. I think Angelina is telling the correct number, but I don't have it here. Okay, so that's 2835. Perfect. So those are actually all of the possible pairs that we can have. Though this is the number of the possible ordered pairs that have this as a least common multiple. Okay. And we didn't even have to count them. See, they are too many. If we were to go ahead and count them by hand and say, okay, then it is, let's say, 2 times 5 times 11 to 13th, blah, blah, blah. We would take 20,000 years to figure it out. But now we figured it out very effectively with just a few observations, okay? Angelina is saying, I don't think you did the plus 1 divided by 2 for this problem because just reverse 10 times 2 plus 1. Yes, the other part that Arman is doing, he wants to figure out the unordered pairs. Okay, but to figure out the unordered pairs, you don't have to add, you have to subtract. Right? You have to do 2835 minus 1 divided by 2. This is what we discussed before. Okay. So is it 1417? Sounds correct, yeah. So these are the unordered pairs. All that we're doing with the unordered pairs is that we are killing the one. Actually, we are killing the one that has the least common multiple itself. So we are killing this one, and then we are dividing by 2 to kill all of the mirrors of the ordered pairs. Okay. So actually, we managed to figure out how many ordered pairs we have for this, which is 2835. And then we even figured out the unordered pairs, which we subtract the one that has both entries are the same, and then we divide by 2 to kill all of the mirrors. Okay. And that actually concludes our mission. Okay. Yes, that's all that I wanted to say. So thank you for your attention, and we can go now over to Ben, who has
Awesome.
very interesting stuff to say. But
All right, so it appears I'm frozen. And now Zoom is freezing. Can you guys hear me just fine?
we can hear you, yes.
Okay.
I can
Oh,
hear you at least, but you are freezing, yes.
of course, that's what happened right when I start trying to share. Let me close the Zoom on the desktop and I'll bring it back up. Give me 2 seconds.
Yes.
I'm back. There we go. Okay. So, I have something to share. We've got our challenge problems, but first I want to do some reflection on what we've been doing. Coming outside of school to work on math problems, that's impressive. Some people think that there's a specific definition for a mathematician. You aren't a mathematician unless you're doing hard math. You aren't a mathematician unless you've been published. You aren't a mathematician unless you have a PhD, but I disagree. I think you are a mathematician if you do math. We've covered a lot of stuff. We've heard from a lot of different people. Think to yourself, how have you grown mathematically? Perhaps it's not just you've learned a new topic, you've learned a new trick, but maybe you've learned a new way to think, a new way to approach a problem. I think the most important thing that y'all have built up is your intuition. Intuition is something that you have that helps you predict an answer without needing to be told or shown how. It's not some innate thing fixed at birth. The more you see, the more you do. For example, musicians. If you play a lot of different pieces of music, you're going to be pretty good at sight reading. I can give you a piece of music and you'll play it pretty well. You're like, oh, that's a minor fifth right there. There's a scale right there. I know what that is. And you put it all together. Practicing your math skills in a lot of different topics helps hone your intuition. You've got a lot of different things to pull on, a lot of different things to think about, and it really helps you when you're given a new problem that you've got no idea what to do. So, before I do this, I need to change some things. Need to remove co-host. And I'm going to change the chat settings. Okay, so currently you guys are only able to chat to me. And that's the way it's going to work because I've got 9 problems here. We'll try and get through them all. I'm going to ask you the question. You'll have a few minutes to work on it, think on it. If you think you know the answer, type it to me in chat. After the couple minutes have passed, we'll pull it up and we'll see who got it right and give them an opportunity to explain. I'm also going to be keeping track of how many times people get it correct, and then Dr. Kwan's going to give you your prize. If you're incorrect, and this is the be very sure you know what you're saying, you got to wait till everybody else has had an opportunity to answer. So don't just guess. After that, we'll discuss how to answer that question. Now, something I don't have on here, I'm going to have a little hint before each problem we're going to talk about. Feel free to unmute, say whatever you like when we're talking about the hint. It's in a topic directly related to that question. So let's start. Here's the first hint. I've got 2 numbers, A and B. I don't know what they are, but I know A is bigger than B. Does someone want to tell me which inequality symbol I can put in between 1 over A and 1 over B? You can unmute, shout it out. See, y'all are chatting. Good. Okay. And I see a couple different answers. And let's talk about this. In this particular example, 1 over A is less than 1 over B. Let's talk about why. Let's pick 2 numbers where one is bigger than the other. 3 is absolutely greater than 2. If I want to compare 1/3 and 1/2, if you're offering me 1/2 of a pizza, I'm happier to take that than 1/3 of a pizza, because 1/2 is totally greater than 1/3. So this is our hint. First challenge problem begins. That was anticlimactic. There we go. So, you're going to tell me which is greater, and you're going to have to justify it. I see a couple quick answers already. Very good, but take your time. I'll even put the hint here. Now, this hint doesn't directly solve the problem, but it gives you a step on the way. I see some more good answers. I see some more good answers. Last call, we'll get about 30 seconds. Type these in, and awesome. Angelina, you were quick. That was good. You want to unmute? Tell us how you worked this out?
I just basically used the hint for this. I just saw that 2022 on the bottom is greater, so than the other one. And then I just thought that that would be just a greater, like, I don't know. I just think that the right one is greater. Because
So you've got the right intuition. Absolutely. 2022 is absolutely
how to
bigger than
explain.
2021. Let's see. I'm gonna... Who else? I see Armand got it right. Armand, do you want to give an explanation? Maybe write out some algebra or just say it out loud?
Basically, what I did is I looked at both fractions. So 2021 over 2020, or 2020 over 2021 and 2021 over 2022. And I could immediately look at 2021 over 2022 because there's a bigger numerator and a bigger denominator than 2020 over 2021. And if you have a bigger denominator, you have more chance of that number most likely being greater than the other if the numerator is at least maybe a couple of numbers away from the denominator. So you most likely have a chance of seeing that number as maybe a larger or a greater number, but slightly, because it's only a digit away from the denominator for both problems.
Very interesting. Thank you. One way that I would write this, so we're talking about our intuition. We have ideas. I want to rewrite both of these numbers in a way that I can directly use this. Because we said this was a hint. And in particular, my hint had ones on top. So if I can rewrite this in a way where I have ones on top, that's going to be awesome. If I consider 2020 over 2021, that looks a lot like 2021 minus 1 all over 2021, right? 2020 is just 1 less than 2021. And I want to rewrite it this way because if I split it up, we notice something simplifies. This left-hand side, this left-hand term is just 1. So 1 minus 1 over 2021. Let's do the same thing with the other. 2021 over 2022. That's 2022 minus 1 over 2022. Split it up. Notice that term cancels again. And I have 1 minus 1 over 2022. And here's where the hint comes in. Notice these terms are the same. It's both 1 minus something. And I can't judge which one is bigger unless I know which one of these is bigger. And I know 2021 is less than 2022. So 1 over 2021 is going to be greater than 1 over 2022. And now I know for certain if I'm subtracting a bigger number, I'm smaller than the other. That happens here. So 2020 over 2021 is smaller than 2021 over 2022. So a lot of good answers, a lot of good intuition. Great job, guys. Do we have any questions or thoughts on this one before we move on? Cool. All right, second hint. How can we compare these two numbers? Notice they're products. Think back to your skills in prime factorization. Because sometimes math just involves knowing whether or not you can say anything about two objects. Maybe you can say one is less than the other, or maybe even best case, maybe they're equal. The Angelina got it right away. Awesome. And here's why this is a great example. These are actually equal. Let's consider the factors on the left and the right number. They've both got two 100s in them. So any differences between these two numbers are not going to show up in those 100s. 3 times 4 is 12. 2 times 6 is 12. Those are the same too. So these numbers are equal. Knowing that we can compare numbers by looking at their factors, here's our second question. And I want to preface the second question. I'm going to ask you two things about it. Make sure you answer both. Here's question 2. Which is greater between those two numbers? And, that's the important part, by how much is that one greater? So take some time. Think about it. No, we do not want to solve. These numbers are large. We can pretend we're living 100 years ago with only an abacus, and I don't want to multiply these out. We're spoiled today with calculators. I see somebody got part of it, but we want to hear both. I see one. Yeah, that's good. Somebody's got it. Somebody else has got it. Very good. It's going to be a little simpler to find out which one is greater. It might be a little tricky to find out by how much. Awesome. I'm seeing a lot of good stuff. Adip, you were first to give me the full answer. You want to give me an explanation? I cannot hear you. Can anybody else hear him? Maybe it's mine.
Oh, can you hear me?
I can hear you now. Oh, yeah.
Okay, so we know that 3 times 4 is the same, is equal to 2 times 6. It's just that if you look at the on the right multiplication problem, you see that it's 6, 6, 6, and then it ends with a 7. And so because of that, it's increasing like full 2, 2, 2, like it's increasing the full like extra 2, 2, 2, 2, 2. The 6 is because of that 7 at the.
And how did we find out by how much greater? It takes a little bit of trick.
Because multiplication is basically repeated addition, right? So in a way, so 6 times 2 is the same as 6 plus 6. So when we had a 7, it was a 1 increase. So because of that 1 increase, we know it was an extra.
Wonderful. I could not have asked for a better explanation. That is exactly what's going on here. We can even rewrite this in a form very similar to this one. Notice we had an almost prime factorization, not quite, but if I want to factor these, I can pull out a 3 of this repeated 3s, and I get a bunch of 1s, 1, 1, 1, 1, 1, 1, and then times 4, 1, 1, 1, 1, 1, 1. Let's group it together so it looks a little bit more like the previous one. Let's put the 3 and the 4 together. And let's put these 1, 1, 1s off to the side. Do something similar with the 2s and the 6, 6, 6, 6, 6, 7. I can pull a 2 out of the first factor, but there's an issue here. 6, 6, 6, 6, 6, 7. I want to rewrite that. 6, 6, 6, 6, 6, 6 plus 1. Now, if I factor out from here, the 6, 2, 1, 1, 1, 1, 1, 1, times big parenthesis 6, small parenthesis, plus 1, we're getting closer. I still can't easily figure out what is that 1 doing. I know it's making it bigger, but by how much? Let's distribute. That's 2 times 6 times 1, 1, 1, 1, 1, 1. That was this times this. Now we'll do the other. This times 1. I have a plus 2, 1, 1, 1, 1, 1, 1, times 1. That one's not doing much of anything. And now we notice this and this are equal. But I've got this guy. 2 times 1, 1, 1, 1, 1, 1 times 1. That is exactly how much greater this number is than this. And that equals 2, 2, 2, 2, 2, 2. I forgot 1, 1, 1, 1, 1, 1, 1. I did. Thank you. Right here. 1, 1, 1, 1, 1, 1. Now they match. Because we have 2 factors here, we better have 2 factors here. But an excellent question. These kinds of number theory problems are wonderful because you get a good number sense for how much bigger things are than the other without actually having to calculate it out. Do we have any questions or thoughts on this one? Looking good. Okay. For the third hint, I'm going to multiply some stuff out for you. And I want you to see if you notice something cool about any of these products. Notice, these are all perfect squares. It's a number times itself. When I do 23 times 23, I get 529. Okay, sure. 11 times 11, I get 121. 111 times 111 is 12,321. And 222 times 222, 49,284. Now, I see something interesting about two of these. They've got a nice pattern in the resulting product on the right-hand side. Seems like I'm counting up from 1 to 2, and then back down to 1. Counting up from 1 to 2, up from 2 to 3, back down again. Notice, you might do these first two and compare it to this 23 squared and think, oh, any number repeated times that same number repeated, 77 times 77, that's got to be cool. I mean, I'm sure it's cool. I won't talk bad about that number behind its back. It's not as cool as these two. We see that exactly here. If I do 222 times 222, I'm sure there's something cool going on, but I can't see it. So I like these ones. Something cool happens there. Here's our question. Does there exist a perfect square that ends in 9 digits? So recall, a perfect square is just a number squared. Is there a perfect square that ends in 9 distinct digits? So all the last 9 digits are different from each other. This one, there's no shame in using a calculator, but you might be able to use your intuition from before. And now I'm seeing some messages. I want to clarify something. Maybe this is my fault for the wording, but it said ends in 9 distinct digits. So if I do 1, 2, 3, 4, 5, 4, 3, 2, 1, I think that's 11,111. This ends in 5 distinct digits. 5, 4, 3, 2, 1. These first 4 are not distinct. Still got 1, 2, 3, 4 inside there. I want something that's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And maybe it has some stuff in front. But it's got to be a perfect square. Y'all were so close in the answers you gave me. You're right on track. But still, I'm not. Ooh, I see something. Okay, I see a dip, got it. And I also see Erica, Kai, Angelina, you guys found the perfect square. Can you also tell me what factor squared that is? Awesome. Yeah, awesome, great. Erica, Kai, got it. So let's reveal. Let's think about the pattern. 11 squared is 121. It ends in 2 distinct digits. 111 squared. Let me check. 1, 2, 3, 2, 1. 3 distinct digits. Now this 2 and this 3, they're not coming out of thin air. Specifically, it's the number of ones. If I want 2 distinct digits, give me 2 ones. If I want 3, give me 3 ones. So if I want 9 distinct digits, give me 9 ones. And the really nice property about these ones, 11s, 111s, it follows an ascending and then descending pattern. This is an absurdly large number. But we don't care how big it is. We only care about the patterns. We want a 9 distinct digit. That's specifically these 9 digits here. Now there probably exist more, but these ones give us the property every digit is going to be distinct on the way up and on the way down. It's very fun, a nice pattern. Let's move on to the next hint. I've got 5 integers here. -5, -2, 8, 12, 20, sure. If I pick 3 at random, what is always true about the sign of their sum if I add them together? Couple people getting it. Always positive. Awesome. Great job. Yeah. With this specific collection of integers, no matter what 3 I pick, if I add them together, I'm going to get a positive value. This isn't true for all collections, but special collections. Here's our question. You have 2002 integers. You have no idea what any of them are. All you know is you have 2002 of them. And any 100 integers that you pick and add together, their result is positive. Use that to explain why the sum of all 2002 integers must be positive. This one will take some words, that's fine, but carefully phrase your thought. I'm seeing some ideas. I'm going to give a little hint here. So of these 2002 integers, if I know the sum of any 100 of them is positive, how many non-positive numbers can I actually have? Because this has got to work for any 100 of them. What if 100 of these integers are negative? What happens there? If I add those up, do I get a positive value? Good, good, I'm seeing that. So 100's out. Whoever's taking attendance, Jacob just said bye. I got a couple good answers. Could be 99. Sure. That's absolutely correct. 100 doesn't work. They could all be negative. But 99 of them could be negative, and that other integer could just be so large. Like in the hint, 8 is larger than the absolute value sum of those two numbers, right? You get a -7. 8's bigger than +7. Same thing here. I could totally have 99 negative numbers. That last one's got to be real big. So, this is already positive. If I take my 99 negative plus my one really big one. Is positive. Do I have any more negative numbers in this set of integers? I already asked how many could there possibly be. Do I have any more negative numbers in that set? I'm seeing some yeses, but I say no. There we go, I see some no's, yeah. 99 is the maximum count of negative numbers I'm allowed to have. I've got them all right here. Those are all my negative numbers. I know I can't have a 100th negative number, or else its sum wouldn't be positive. So already collecting all my bad negative numbers, I have a nice integer that makes the sum positive. And the rest of the numbers, because this is 100, I've got a total of 2002 integers. If I add the other 1902 integers, which we already know is positive, because all the negatives are right here, if I add these numbers to this result, well, it's already positive. Add a bunch more positive numbers, it's going to stay positive. So this one's a little tricky. Problems like this are nice. You get a good number sense and groupings, some combinatorics, you get a little flavor of different styles of math. Now it's 8, so I think question 5 might have to be the last one. I'll give you your hint. And actually, I don't like this one. Let's do... I like 7. 7's a good one. Here's your hint. You got 9 pairs of socks in your dresser, and I assume you have 2 feet. If you can't see anymore, right, everything's dark, how many socks do you have to blindly grab from your dresser to guarantee you've got at least one matching pair of socks? Because you want to look good. Feel free to shout it out, chat it out. It brings up a good point, even though no one can see you, but you dress for success, you know? You know you have matching socks, so you're happy. Now, I haven't seen the right answer yet. So you got 9 pairs of socks, so right, 18 total socks. Assume they're all different pairs. You got a white pair, red pair, blue pair. Ah, Erica and Kai, you got 10. Nice. Awesome. It is 10. If you want to look this up, it's called the Pigeonhole Principle. It's a really cool math concept. It talks about collections and sets. And the first time we ever see it is typically with this problem. If I pick just 9 socks, there's a chance, albeit small, that I pick one of each pair. I've only got 1 white, 1 red, 1 blue, 1 yellow, 1 green, 1 orange. I don't match. But if I pick 10 socks, no matter what, I'll have at least one of everything and then the extra. We don't know what color it is, but we know it matches another. So I want 10 socks if I have 9 pairs. So there's our hint. Here's our last challenge problem. You have 11 natural numbers. Natural numbers are positive integers. Convince us that there must be, in this set of 11, 2 numbers whose difference is divisible by 10. we'll give you a starting point. We don't know how big those natural numbers are. But any natural number, its last digit must be either a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, or a 9. I don't particularly care about what comes in front. All I know is it ends in 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. How many options do I have there for natural numbers at the end? Yeah, 10, 10, very good, because there are only 10 single-digit numbers. You could make an analogy. These are just like socks. These are your different colors of socks. You got a yellow, you got a red, you got a blue, etc. How many do you have to pick so that two numbers end in the same digit? 11. Now that's part of it. Let's say they happen to end in 3. They're wildly different numbers. They've got different digits in front, but they both end in 3. And so close. If we subtract them, what do we get? We don't exactly get 0, but what does the last digit of their difference equal? It ends in 0. Very, very good. I don't know what I get, but I sure know it ends in 0. And any number that ends in 0, what do we always divide it by when we're doing factorization? 10, yeah. Awesome, awesome. Okay, wonderful. So I think we're a little short on time. We might have to call it here. But thank you all for letting me be your last presentation in the Math Circle. Let me fix the chat. Yeah, there's a prize. I'm keeping tally. I lied. I'm not keeping tally. It was impossible. I have the chat saved on the computer, and I'm going to go through and tally that up, give it to Dr. Kwan, and she's going to announce it at some later date. So I've fixed the chat. You all can now chat to everyone. Before you could only just chat to me, and I'm going to make the rightful people their hosts. I believe that does it. So again, this is an example to develop your intuition. Just because you've never seen these problems before doesn't mean you don't know how to do them. You might have an idea. And the more stuff you see, the better you're going to get at new and interesting problems. Thank you all.